Welcome to this explainer. Today, we're taking an absolutely incredible journey. We're going to shrink ourselves way down, traveling from the everyday technology you're holding in your hands right now, all the way down to the fundamental, atomic level of the materials that make it all possible. To put this into perspective, a single human hair is roughly, 80,000 to 100,000 nanometers wide. But today's most advanced transistors, they're being built on scales approaching just 2 or 3 nanometers. It's wild. We are literally manipulating matter at the atomic limit to build the modern world. So let's explore the magic of semiconductors.
Let's kick things off with a simple but completely mind-bending question of scale. How is it that a modern pocket-sized smartphone or a super sleek laptop totally outcomputes the massive, room-sized systems that literally put humanity on the moon? Think about it. The Apollo guidance computer ran at roughly 2 megahertz with only about 4 kilobytes of random access memory. Meanwhile, the device you're likely using to view this explainer right now, it contains billions of individual transistors, processing trillions of operations every single second. It is a staggering comparison of power and efficiency.
While the secret to that incredible leap, the true foundation of the information age, lies entirely in semiconductors. Specifically, it's our ability to transition from the macroscopic world down to the microscopic. Just think back to early computing that relied on those bulky vacuum tubes. They were massive, they consumed immense amounts of electricity, generated debilitating heat, and they constantly burned out. But moving to microscopic, solid-state semiconductors, that allowed us to pack millions of integrated devices onto a single tiny chip. And this didn't just shrink computers down, it drastically reduced power consumption, massively increased reliability, and it unlocked this exponential scaling in computational density. A total game changer.
Okay, let's dive into this. Here's our flight plan for today. 1. The semiconductor revolution. 2. Fabricating a microcity. 3. The p-in junction blueprint. 4. 3 types of solids. And 5. Inside the crystal lattice.
Section 1. The Semiconductor Revolution, from early detectors to the information age.
Let's start with a broad historical look, really just to understand the sheer velocity of semiconductor evolution. Back in 1874, Ferdinand Braun discovered the asymmetric conduction of metal semiconductor contacts. That was a principle that eventually powered early radio detectors. Fast forward to 1947, and we see a massive paradigm shift. Bell Labs creates the first point contact transistor, a solid-state device that effectively signaled the death of those fragile vacuum tubes. But there was still a problem. The real structural bottleneck, what engineers famously called the tyranny of numbers, still loomed over them. Because complex circuits required hand-soldering thousands of individual, discrete components together, and the failure rate of these manual connections, absolutely disastrous. That is exactly why 1959 was the true game-changer. Jack Kilby and Robert Noyce independently developed the integrated circuit. Instead of wiring separate devices together, they realized they could pattern complex, continuous circuits directly onto a single, unbroken chip of semiconductor material, effectively solving that tyranny of numbers forever.
Moving into Section 2, Fabricating a Microcity, Manufacturing at the Microscopic Scale.
So how do we actually put millions or even billions of devices on one chip? Well, imagine we aren't just building electronics. It's more like we're constructing a highly complex microcity, layer by microscopic layer, inside incredibly controlled cleanrooms. And this brilliantly illustrates the beautiful, complex progression of silicon wafer manufacturing. We don't just find this material out in nature ready to go. It usually starts with a process where highly purified molten silicon, at over 1400 degrees Celsius by the way, is carefully pulled to form a massive, perfectly structured cylindrical ingot. That heavy ingot is then sliced up with diamond wire into incredibly thin wafers, which are then mechanically and chemically polished to absolute mirror-like perfection. These pristine wafers serve as the raw real estate upon which our integrated microcities will be built.
To build our microcity, we rely on a sequence of highly specialized construction phases. First up is thermal oxidation. And we aren't just laying down an insulator here. Actually, we are growing a pristine layer of silicon dioxide directly out of the silicon itself. The magic here is that the interface between the silicon and the dioxide is remarkably defect-free, which keeps stray electrons from getting trapped at the surface. Next is photolithography, which patterns out exactly where our active regions will go. After that comes etching. We use advanced plasmas to physically and chemically carve deep, perfectly vertical trenches into the material, removing unwanted sections with literal atomic precision. And finally, doping or diffusion. By raising the temperature to roughly 1000 degrees Celsius, we increase the thermal kinetic energy of the silicon lattice. This allows specific impurity atoms, like phosphorus or boron, to literally sink right into the crystal structure, fundamentally altering the electrical conductivity in highly targeted microscopic zones.
Let's isolate photolithography for a moment, because honestly, this is the magical step determining the absolute physical limits of our devices. We coat the silicon with a photoresist, an organic polymer that goes through a chemical transformation when exposed to light. We then shine light through a photomask, which acts like an incredibly intricate stencil. But we aren't using normal light here. To achieve modern transistor scales, we use extreme ultraviolet light, with wavelengths spanning just mere nanometers. The dark areas of the mask block this light, while the clear areas project the microscopic blueprint directly onto the photoresist. And what is truly awe-inspiring here is the sheer scale of replication. I mean, this single optical exposure allows us to flawlessly print billions of identical, nanoscale features across the chip simultaneously. It's incredible.
All right, Section 3. The PN junction blueprint, building the fundamental device.
Now, what's really interesting about this is what happens once those master blueprints are imprinted via photolithography. We use them to build the bedrock device of all semiconductor physics, the PN junction. Every solar cell, every LED, every processor relies on this fundamental structure. Take a look at the 8-step fabrication blueprint on the left, contrasting with the precise mathematical result on the right. We start with oxidation, apply the mask, etch the window, and introduce the dopants. But look closely at the resulting concentration of diffused impurities. It isn't a hard binary line. Because diffusion relies on a concentration gradient and thermodynamics, the impurity atoms move into the silicon to create this beautifully graded, nonlinear curve. This specific mathematical grading is critical. It determines the precise width of the depletion region, which in turn directly controls the breakdown voltage and capacitance of the junction. We are literally using physical manufacturing to dictate pure functional physics. Section 4. 3 types of solids. Shifting focus to physics.
Now that we've mapped out the manufacturing side, let's completely strip away the clean rooms and the chemical etchants. We need to look at the fundamental material physics that actually allows a semiconductor to function. Solid materials generally fall into 3 categories based on atomic order. Amorphous materials are highly randomized. They exhibit structural order only across a few molecular dimensions. Polycrystalline materials are more structured, with ordered regions spanning many atomic dimensions. However, these ordered regions form grains that constantly crash into each other, creating what we call grain boundaries. And for high-performance electronics, grain boundaries are the ultimate enemy. They act as scattering points and recombination centers. When an electron tries to move through the material, it hits these boundaries, loses momentum, and generates excess heat. That is exactly why the holy grail of semiconductor manufacturing is the single crystal. In a single crystal, the regular geometric periodicity extends flawlessly throughout the entire volume of the material, completely eliminating those disruptive grain boundaries.
Visualizing this in 2D makes the contrast undeniably clear. Look on the far left. The amorphous material is just a chaotic, randomized scattering of atoms. Moving to the middle, the polycrystalline material has distinct regions of tight order, but they're fractured, right? They're pointing in different directions and broken by those disruptive boundaries that kill carrier mobility. Now observe the single crystal on the right, perfectly repeating, beautifully ordered, entirely uninterrupted lines of atoms. This unbroken, pristine order is critical because charge carriers, electrons and holes, need a ballistic, unhindered path to switch states in fractions of a nanosecond without losing energy. This perfect crystal canvas is quite literally the physical medium upon which all modern computing power is painted.
Which brings us to Section 5, inside the crystal lattice, the foundation of the microworld.
So the crucial point here is that we have reached the absolute foundational level of our journey. Zooming in past the integrated circuit, past the graded PN junction, we finally arrive at the underlying atomic geometry of that flawless single crystal. And we need to establish the vocabulary of this atomic realm. We mathematically represent this perfect order using a space lattice. Take a moment to really consider what this represents. An infinite three-dimensional array of points, where each point defines the exact location of an atom or a specific group of atoms. The space lattice isn't just an abstract grid. It is the rigid mathematical backbone that ensures electrons behave predictably across billions of repetitions in a silicon wafer.
And within that infinite mathematical grid, we isolate the unit cell. This is a small, fundamentally representative volume of the crystal. But don't just think of it as a single static brick in a building. The unit cell is a localized mathematical blueprint. The defining characteristic of a unit cell is that if you take this microscopic 3D geometric arrangement and translate it, meaning you repeat it continuously along its axes in 3 dimensions, you perfectly reproduce the entire macroscopic crystal lattice.
This means that by understanding the quantum mechanical properties within this single microscopic unit cell, you effectively dictate the macroscopic electrical, optical, and thermal properties of the entire full-size silicon wafer we started with. It's mind-blowing when you really think about it.
Which brings us to a final, awe-inspiring thought. Next time you pick up your phone or type on your laptop, remember that you are quite literally holding billions of perfectly ordered atomic lattices right in the palm of your hand. These are structures that have been painstakingly grown from molten rock, carefully doped with precise impurity gradients, meticulously sculpted by extreme ultraviolet light, and are currently communicating in fractions of a billionth of a second. As we continue to push the absolute boundaries of physics, striving to pack more and more power into smaller spaces, what will the next leap in miniaturization even look like? When transistors reach the width of just a few individual atoms, how much deeper can we possibly go? It is a profound question, and one that drives the very future of the information age. Thanks for joining me on this explainer, and keep wondering.